Yes.
Okay, so the next talk is going to be by Mar González from Madrid about the Levy Fokker-Planck equation.
Okay, so first of all, I would like to thank the organizers for the opportunity to give a talk here. I was here maybe 14 years ago, and I think it's as beautiful as always. And about my talk, I'm going to talk about Levy Fokker-Planck equations. I'm going to look at the spectrum. And I apologize in advance if my talk becomes technical at times. I'll try to give you the main ideas, but bear with the huge formulas. So a quick introduction. So this is my equation. I'm going to consider the following operator L. It's given by the fractional Laplacian of u to the power s. If you don't know what the fractional Laplacian is, just I'll give the definition in a couple of slides. And then I add a plus minus drift term of this form. Then I add a first order term which will not play any role in the spectrum. So basically, and you see here I put a plus and a minus. There is a good case and a bad case, but our methods will be able to deal with both. So basically, keep in mind, I have a combination of a fractional diffusion and a first order drift term. So the diffusion gives you regularity of order 2s. And the drift is of first order. So you see that there is a competition, and for s equals 1/2, they have the same order. So sometimes this one wins, sometimes this one wins. But my first comment is that this theory is valid for any s between 0 and 1. So of course, when s is greater than 1/2, diffusion wins and you have the standard elliptic theory. But when s is less than 1/2, you still have good regularity properties. Now, my second comment is that in my talk, I will talk only about radially symmetric solutions. This is functions u that depends on r, where r is the radial variable. Now, I could do a spherical harmonic projection, and I could to decompose this in eigenfunctions and spherical harmonics. So we didn't develop the theory, probably, I mean, one can do it, but let's concentrate on the radial case. So let's take this equation in the radially symmetric case. So objectives. Now in this talk I will do the eigenvalue problem. So okay, I'll explain. I'll calculate the spectrum and prove compactness, and then okay, maybe I can talk about regularity estimates, but let's mostly I want to do the spectrum. And this is joint work with Hardy Chan, Marco Fontelos, and Chun-Ching Wei. Okay, so now a quick review of the fractional Laplacian. So this is just an operator that represents fractional diffusions, and from probability it is the infinitesimal generator of a Levy process. Now here we are looking at its Fourier definition up here. So the fractional Laplacian is a pseudo differential operator defined by this relation. When you take its Fourier transform, you see that its symbol is just c to the 2s then times the Fourier transform of f. So you see here, if you only had the Laplacian, then the symbol would be c squared. When you put the s power, you define by this operator, by the operator that the inverse Fourier transform of this object for s any number between 0 and 1. Okay, it could have other values, but let's concentrate between 0 and 1. Now, from the harmonic analysis point of view, it also has a singular integral formulations in which you calculate the fractional Laplacian of a function at a point x. That's the principal value of the following integral. I'm taking the convolution of my function with this singular integral in this singular kernel here. Now, the first comment about this definition is that this is a non-local operator, because to know what happens at a point x, you need to know the values of the function at the whole space. So that's why we say it is non-local. Now, there is also an extension viewpoint to understand this operator developed by Caffarelli, Silvestri, and collaborators, but I will not need it for my talk today. And something that The origin of this problem actually comes from my work, my previous work on conformal geometry, and also in the thesis of Azahara de la Torre. But I will not I will not talk so much about conformal geometry. Okay, so let's go back to our problem and let's see where it comes from. So we look first at the fractional heat equation when you have the time derivative of a function and a fractional diffusion for positive time, and then consider self-similar variables for the heat equation. This is just the usual self-similar change where you change the time with a logarithm and this rescaling for the space variable. And what you arrive with this change of variables is at the following equation in which you have time evolution, you have the fractional diffusion, and you have the drift. So here, this is the operator we are interested in with a minus. Now, another application where my operator comes from is when I look at finite time blow-up solutions for the heat equation. So when I look at the fractional heat equation up here, and I look at solutions that blow up at a finite time capital T, if I make this change of variables to understand what happens near the blow up, say I change T with this definition and also I rescale space, what I arrive after the change of variables is this equation where you see that we are getting the L operator again, our operator, so fractional diffusion plus drift. Now the difference between these two is that this one here comes with a minus and this one here comes with a plus, but still our methods work for the two operators, and essentially one is the adjoint of the other. Now there is some zeroth order term that comes up, but it's not going to be important. Essentially these two problems are adjoint, and if you understand one of them, then you understand the other. And in some sense this problem is better behaved than this one. Okay, so here is our main theorem. I recall what my operator L is. Remember that we are working only with radially symmetric solutions, so I have my operator that is a sum of a combination of a fractional diffusion and a drift term, okay, plus the zeroth order term. So my main theorem is that L has eigenvalues mu equals k, so the eigenvalues of this problem are only the non-negative integers, so just the natural numbers and the zero, and the eigenfunctions can be explicitly calculated as, okay, you have some power, some negative exponentials, and this Lk here that, okay, don't worry about the precise definition, but there is some kind of generalized Laguerre polynomials. Now, important thing is that these eigenfunctions for a complete orthonormal basis, and then you can do a separation of variables, and standard like spectral decomposition works for this problem. Now, that is okay. I have to tell you what the function space is. I'm going to introduce this new space dagger that it's the L2 norm of the function times this, okay, with this exponential weight. Now, this theorem would be very nice, it would be heaven, but the first thing you realize is that the kernel, the Gauss kernel for the fractional heat equation doesn't have exponential decay, so you don't expect an exponential weight because you expect some power. The heat kernel has only power weight at infinity. So what is the catch? And you see here, I wrote theorem star, and I was very careful to write the problem with U and to write my theorem with some W. So the difference between this U and this W, this star, is that it's up to a change of basis that I will explain in my talk. But up to this change of basis, I have a complete characterization of the spectrum. And then you can do separation of variables or whatever. Okay, so let's let me look at the local case when you don't have any non-local operator and you just have the Laplacian and a drift. Okay, let's look at the eigenvalue problem. So let me call the eigenvalue nu. And the first thing we observe, this problem is set up in the whole space Rn. Okay, radially symmetric solutions, but in Rn. The first thing is that if you work in bounded domains, the W12, the Sobolev space W12 is compactly embedded in L2, but this is false in general in Rn unless you introduce an exponential weight. Then with this exponential weight you recover compactness. So this compactness is the one that allows to say that, okay, this problem is going to have a discrete set of eigenvalues, and there will be an increasing sequence like a regular elliptic problem. Now, how to find this, this spectrum? Look at the equation and take Fourier transform. So here the Laplacian gives, but one second, the Fourier transform in Rn, since if xi is the Fourier variable, and since we are only talking about radially symmetric solutions, its Fourier transform is only going to depend on the radial, on this zeta that is the radial Fourier variable. So now let me rename the Fourier transform of u to be just a function of this zeta variable. Okay, when we take Fourier transform, the Laplacian gives me Fourier zeta square phi, the drift term gives me also this first order term, and then this one stays the same. And if you look at this equation, this is just a simple ODE in the zeta variable. You solve this ODE and you know that your eigenfunction or your tentative eigenfunction at eigenvalue nu is given by this function. It's explicit. Now, not all of these are eigenfunctions. Now we have to choose which ones are in the right functional space. And the right functional space is this L2 with the exponential weight. So, if you put this exponential weight, it means that your eigenfunctions must decay at infinity up to all orders. Okay. So, if we impose the exponential decay for the eigenfunction as at infinity, when looking at the Fourier transform, this translates into a smoothness at the origin for its Fourier transform. So then this phi that I have here must be smooth at the origin. Okay, this is smooth only when nu is a non-negative integer. So actually you have found explicitly the eigenvalues of the problem, and if you take the inverse Fourier transform of this guy, at least let me give you the formulas in dimension 1, you see that your eigenfunctions are reduced to Hermite polynomials, and they are explicit. So in the local case, this is just a simple calculation. Let me see what happens in the non-local case when you put a fractional diffusion there. So I have here my fractional Laplacian, my drift, and I'm looking at the eigenvalue problem. The first thing is that we have no compactness. So we didn't know, we didn't have compactness at first. Because, as I explained, the heat kernel for the fractional heat kernel does not have exponential decay. It only has power decay. So it is not natural to introduce exponential weight at this space. Now, I could say, okay, let's be naive and take the Fourier transform of the equation. Again, I call zeta the radial to be the radial Fourier variable, and the Fourier transform of u to be this phi. When I take the Fourier transform of the fractional Laplacian, the symbol is zeta to the 2s, then there is the first order term, and then nu phi, okay, same thing as before, and this ODE has an explicit solution that is very similar to the one before. Now, but but now we cannot play the game of saying, oh, I impose exponential decay of the function I mean, we don't know what we cannot play the same trick of imposing decay of the solution to find the values of nu who are real eigenvalues. So basically we have a nice formula, but it's not helpful. It doesn't. Now, an important observation, and this is a very naive idea that we have later found in some physics papers, like they do a few things with this equation, is that if you look at this eigenfunction and take the change of variable zeta to the s to be z, you recover in the new variable these eigenfunctions that they look like the eigenfunctions that I presented for the local problem. So naively, this change is changing from the S problem, a non-local problem, to the classical problem. So if you know how to solve the classical problem, by this change you will be able to do something with the non-local case. And this was our guiding idea at the beginning. Now, in any case, this naive idea, it doesn't help to either find the values of mu who give you eigenfunctions. It doesn't tell you who the function space is, so we couldn't do anything with the Fourier transform, and all our results are written in terms of Mellin transform. I don't know if you have heard about Mellin transform before. Let me give you a quick review of the Mellin transform. So now, let U be a radially symmetric solution, so let's say as a function of R. Its Mellin transform is an integral transform. Let's call it mu of z. Z is going to be a complex number. It's the Mellin argument. Is the integral of the function against this r to the z times dr over r. So it's not so different from Fourier transform. And actually, if you look at this line, before. It is customary to write the Mellin argument z to be lambda I, where lambda belongs to R, but you can put any other normalization. And actually, one of the reasons why we haven't been able to finish writing the paper is that we have parts of every section of the paper is written with a different normalization, and now we have to sit down and put the same normalization in the whole paper. So that's a bit painful. In any case, with this normalization, the Mellin transform is equivalent to the Fourier transform in a logarithmic variable. Just look at this calculation. The Mellin transform of lambda I, I wrote here the definition. When you make the change of variables t equals minus logarithm of r, you get this expression, and this is like the Fourier transform of this function in the new variable. So Mellin is more or less like Fourier, with a logarithm in the middle. Now, it has nice properties like Fourier transform, so there is a Mellin inversion formula in which from the Mellin transform of U, you recover back U by taking a complex integration. You also have a Plancherel identity in which the L2 norm of the Mellin transform of U is the L2 norm of the function. There are some weights here and there, but just keep in mind that this is the usual Plancherel. And this also allows to define some Mellin-Sobolev spaces in which H beta, it looks like the Fourier definition of Sobolev spaces, like multiply by, put a multiplier here, 1 plus lambda squared to the beta, times the L2 norm of the transform. So if this was Fourier, it would give you usual Fourier spaces. If you put Mellin, it will give you Mellin-Sobolev. And actually, for instance, let me just write. So in the H1 space, the norm is, the integral of U squared plus R squared, the gradient U squared. So you see that Mellin-Sobolev spaces are like usual Sobolev spaces with a different homogeneity. But more or less they're the same. Okay, so now we have a Mellin transformation. Let's see what it does to the fractional Laplacian. And our first proposition is the following, is that if you take the Mellin transform of the fractional Laplacian of U, you recover the Mellin transform of U times this symbol. So basically in Mellin variables, the fractional Laplacian is just a multiplier, same thing as you did with Fourier, except now that this multiplier theta s is a little bit, well, it's ugly, and it's what it is, but two things. This theta of s behaves like z to the 2s when z goes to infinity, so you see that you are looking at an operator like the fractional Laplacian of order 2s, so it's not odd. And this guy has an advantage over this guy in which this is a meromorphic function, while this one is not. So for complex analysis, this is much better behaved, even though you have that nasty formula with the gamma functions. But whatever, it's a meromorphic function. It's a well-behaved meromorphic function. Now, in the paper, we're giving a new proof using Hankel and Mellin transform. The old proof that it was one of the first results in Azara de la Torre's thesis. Comes from conformal geometry, in which let's look at an isolated singularity at the origin. So let me write the Euclidean metric, the r squared plus r squared with theta squared in polar coordinates, divide by r squared. And now let me make the change. This is the usual, the change that brings from Fourier to Mellin. R equals to e to the minus t. When you make this change, you find dt squared plus the metric on the sphere. This is the cylindrical metric. So actually the Mellin transform is like working on cylindrical coordinates. And then since the cylinder is conformal to Euclidean space, you can use the conformal law of the fractional Laplacian or the conformal fractional Laplacian, and actually the conformal fractional Laplacian is an operator PS that I'm not going to define, but from the analysis point of view is like an intertwining operator with the usual Euclidean Laplacian, and the Fourier symbol of this conformal fractional Laplacian is exactly this guy. So in summary, when you do conformal geometry in cylindrical coordinates, it's like, and mixed with Fourier, it's like doing Mellin transform. Okay, so now we finished with the introduction on the Mellin transform, and let's go back to the theorems, back to our eigenvalue problem. So remember, I had to find, this is the eigenvalue problem, fractional Laplacian, drift term, well, zeroth order term, which is nice to write there. And let's take the Mellin approach. So I take the Mellin transform of this equation. The Mellin transform of the fractional Laplacian gives me this funny symbol times the Mellin transform of u. Okay, and now you take the Mellin transform of this, and where you arrive is to this equation in Mellin variables for u, for the Mellin transform of u, where z could be any complex number. Now, the miracle is that if you make these changes of variables, change from the Mellin transform of u to v, I mean, don't ask me how we found this, it was like 2 weeks of trial and error. We reduced this, actually this calculation, we did it during Christmas last year, where everyone was locked up with COVID, like January 2022. So this is when we did this calculation. And in our case, when you make this change in the equation, what we arrive is that v is a periodic function in z. So we are comparing the values of two functions on two parallel lines of the complex plane. And then the only solution is like, well, basically the identity or all the complex exponentials, but basically you have an explicit formula, and when you undo the changes, you see that your eigenfunction in Mellin variables has this precise formula. Okay, more gamma functions, but doesn't matter, it's explicit. If you are able to undo this to take the inverse Mellin transform here, you will get an explicit formula for the candidate of eigenfunction. Still, we don't know what is the function space, but I will get there in a moment. in any case, let's do a sanity check and let's compare the Fourier transform of this guy to the result we had a few slides before, and we see, okay, the two things coincide. The Mellin definition and the Fourier definition are the same, so we didn't make a mistake in the equation. Now, this is new from the last time I gave this talk, but I mean, it's not so important, but actually we were able to take the inverse Mellin transform of this guy and obtain explicit formulas for the eigenfunction, and okay, it is that, but it doesn't tell you much, but it's written in terms of special functions. But this didn't help us to find the function space, or who is that new. So I'll skip this transparency. Let's go to the interesting part, is where we choose the function space and we choose the eigenfunctions. So now, let's recall that we had found by our eigenfunction in Mellin transform, and it had this funny formula, but we have it. And now we are going to decompose this product into two parts. One part that I'm going to call lambda, and one part that I'm going to call capital W. Now the part of lambda, it's going to be what I call the change of basis. And what I call this W is the part that when I take its inverse Fourier Mellin transform, it has a very nice explicit formula in terms of the generalized Laguerre polynomials, and these are the W's that I stated in the main theorem at the beginning. So what I have proved is the first part of the theorem is that up to an isometry or a change of basis, the eigenfunctions of these problems are these ones. Okay, still we don't know that they are only the integers, the k, but at least we have a formula for the eigenfunctions. In any case, lemma is that these wk are a complete orthonormal basis for this scalar product that I introduced at the beginning, that is the dagger space. So in the change, when we use the change of basis, it allows to reduce our original problem to a new problem where we can write exponential decay of the, sorry, this should be a plus, where we have, we can introduce an exponential way to define our function space. So in Mellin variables, okay, up to this change of basis, we have a very nice scalar product where we have compactness. Okay, so now in general, for every nu, not necessarily a non-negative integer, we have an explicit formula for the eigenfunction, and it's okay, it's this horrible thing, and you may just want to look at the second statement of the theorem. When r goes to infinity, W mu in general, if you are not at the non-negative integers, it decays, it has power decay. But when you choose nu equals k, you gain exponential decay. So actually, if your dagger space tells, if you choose your space to have exponential decay, you say, okay, these ones are not eigenfunctions and these are the right ones. So that's how we choose our function space. It's the one that gives, asks in the W notation after change of variables, it gives you exponential decay. Now the proof of this, it's like 3 pages of calculations, but it's not very difficult. Just remember, we had the formula in Mellin variables. It was a matter of take the inverse Mellin transform, which is a complex integration, and apply residue theorem, or a very with a well-chosen integration contour. So conceptually, it's not very difficult. Okay, so now I have to explain who was the change of basis. So, okay, here. So now recall that I had defined the multiplier lambda, well, had a nasty formula, and I call it an isometry. Let's justify why it's an isometry or a change of basis. In particular, the Mellin transform of, okay, this multiplier lambda corresponds to a map capital phi, which is what I'm calling isometry, and I call it isometry because it preserves norm in all Sobolev spaces. Now, depending on the normalization, you can put h beta and h beta here, so this psi s is not changing the regularity of your solution. Now, what this isometry is doing, it has a very nice, here it doesn't give you any, you don't have any feeling of what it is, but it has a nice Fourier interpretation. So let me call U dagger to be the inverse Fourier transform. Okay, take U. Okay, let's see who this transformation phi is. Take U, take its Fourier transform, change the Fourier variable by this zeta to the 1 over s, take the inverse transform U hat, then this isometry is like do all this that I have just explained to get U dagger applied to R2ds. So it's a kind of two changes of power and a game of, Fourier, change variable, Fourier back, and that's it. So we have a very good characterization of this change of basis, or change of variables, or isometry. Okay, so just to, so we have time. So let's look at a little bit more carefully of what this change of variable, change of basis means, and how to find my right function space. So remember that I had defined my dagger space, my right function space, which was given by the scalar product with respect to an exponential weight of the W. So the W is the change of basis from U, so just to keep the notation, that is just a switch between U and W, and this is the isometry. So we want to write this is my right function space. I want to put it in my U variables, in my usual variables, in my usual function notation. Okay, so here W, yes, I isolate W is phi minus 1 of U, so I substitute, and this is my definition of my dagger space in which I have a very good control of eigenfunctions. Okay, what the hell is this? Because this is not exponential decay for the original function. That's the first thing. Let's look at the Fourier. So in Fourier, because remember there was, I just presented some Fourier equivalence, this dagger space is like, okay, this Fourier change variable R2ds, okay, you have a nice interpretation with the Fourier transform that I presented in the previous slide. Okay, but this is still not very satisfying, and okay, you can try to explain this a little bit better by taking a Taylor series of this exponential, write this as the sum of powers, play around with all the r's that come out, and actually what you are getting, just you have to look at this explicit norm, but it's a combination, okay, it's a sum of m, a combination between of derivatives of u and powers. So actually this has been these type of spaces are known in the literature, and this is a version, a fractional version of a Gevrey-Sobolev norm. Usual Gevrey-Sobolev norms are given as the sum in M over, like, you have to look at all the derivatives, M derivatives of U, here I wrote the Fourier definition, times this sum with this exponential divided by n factorial. So somehow this new H dagger space, it's a fractional version of these Gevrey norms. Still, this was not very satisfying because this had a very complicated formula. Now we gave the Mellin version of the space in which the h-dagger space, okay, let's go back to the original definition. We have the change of basis and the exponential. The first thing I'm going to do is to take the Taylor expansion of this exponential. So this is what I'm doing. I'm writing the sum from n equals to 0 up to infinity of Taylor expansion. Okay, there's, I put r to some exponents that depend on m divided by n factorial, and then there is a 4. But anyway, this is just Taylor expansion of the exponential. In the second step, I use the the Planck general identity of the Mellin transform, in which the L2 norm of a function is the L2 norm of its Mellin transform. So that you see, this is the L2 norm, and I put an m here. Now, in the next step, okay, this isometry phi had a very nice symbol in Mellin variables. So this is what I call the capital lambda at the beginning. So this is my definition of the dagger norm. Is the sum in n of some symbol, which, okay, whatever, it has a horrible formula, but we know how it behaves, times the L2 norm of the Mellin transform of U. So it's not bad. And this is actually what allows to get regularity. So these are, okay, I have time. So now we get to, I have given you a definition of a space. I have calculated the eigenfunctions. Let's make sure that the spectrum is discrete and we have compactness, so that we close all this business. So let's look first at the regularity property for our operator Ls. So let me consider the equation Ls of U equals to F. And the proposition is that in some sense, the dagger norm gains somehow s derivatives or 2s derivatives with respect to the dagger norm of the right-hand side. So if you know the elliptic theory, the fractional Laplacian gains 2 derivatives. So the same thing is happening here with this dagger norm. Now it's all hidden. Okay, I have to tell you who this S norm is, but if the H dagger norm was the L2 version, the H dagger S norm is the version with 2s derivatives more. So maybe I don't have to go through the through the definition, but think that it's the same thing that with the usual Sobolev regularity in Sobolev spaces for this simple equation. And actually, the proof of this regularity result, if you take the usual proof for the Laplacian in R or in Rn, and look how you do the proof and rewrite all the integrals in Mellin transform, you can copy the proof line by line. So now, one thing that you have to take into account is, okay, you have a sum, but you can do, well, I mean, you have to put the sum here and there, but really the same proof works line by line. So, okay, now you get the classical regularity result for the fractional Laplacian, except that, look, when S is less than 1/2, you still, the drift is not messing up the regularity of the equation. So that's the important comment. And now compactness, because to have the full spectral theory, you need some compactness theorem. And this is what I'm saying, that this H dagger S space that I have defined before is compactly embedded in H dagger, the same way as this is the replacement of the classical W12 with exponential decay is compactly contained in L2 with exponential decay. but now I have this funny norm. Okay, in the local case, how do you prove this? Then, well, you have to make an estimate where you control the weighted Dirichlet energy from below by the weighted L2 energy, and you see here that you have gained a factor of x squared here. So somehow this norm controls the behavior of u at infinity, and you gain a little bit extra control. And that's the proof, that's what gives compactness in the standard Sobolev space, this x squared that helps you to control the behavior of the function at infinity. Now, in the non-local case, you still have this control, because this H-dagger norm, or actually only the semi-norm part, also controls the L2 norm of the function with the exponential weight. And you see here that you have gained a little bit of power of r. So when S, so this power of r is this power of r that you were having here. So when S is greater than 1/2, you have a little bit of gain that yields automatically compactness. Now, if S is less than 1/2, if S is less than 1/2, this is not enough, and you have to use the drift term, but I don't want to go into the details here, and instead, sorry, not yet. I want to give you the key step of the proof, because here the trick was to gain this extra r squared factor. So the key step, since our norms are defined, so here is the definition of the norm in terms, so remember that I had the Taylor expansion of the exponential, I had the multiplier, and I had the L2 norm of u. Okay, when you try to prove something with this norm, what you are left to do is to take the sum of these kind of things. You see that this m to the 2s comes from the diffusion, from the Laplace 2s, and actually when this sum is more or less rho to the 2s e to the rho, and this rho to the 2s is the extra factor that you are gaining here. So this is the key step of the proof. So it's not so different from the local case, but you have transformed these integral inequalities into, first you have the infinite sum, and then you have replaced all the energy and the norms, but it's Mellin transform. But the steps of the proof are actually the same. And okay, I think we have some other results. So also for the adjoint equation, we have some explicit formulas, but I think it's a good moment to stop. So thank you.